Last time we were talking about the solar system, so we will complete that discussion today, and then we will look at extrasolar planets, which will be the main topic to be covered today. So we looked at these planets, dwarf planets, etc. The smaller components of the solar system include comets. These are icy bodies that release gas and dust when near the sun. And when they are far away from the sun, they don't lose too much mass. They remain as they are. They're composed of ice, rock, dust, and frozen gases. They can have elliptical orbits, okay, which are the closed orbits, but they can also have open orbits like parabolic or hyperbolic orbits, in which case they only visit once, go around the sun once, and then they are gone forever. There are two main types of comets, short period comets and long period comets. The most famous comet is, of course, the Halley's Comet, which is visible every 76 years. So it's coming next in 2061, less than 40 years from now.
So the short period, whatever.
Short periods can be few years, even I think less than a year is possible. But most by short period one means of the order of a decade or less.
So Alice comet would be
Long period comet, yes. Right. And this is the rough structure of a comet. There is a nucleus which is very small, of the order of a few kilometers. Surrounding the nucleus, so the nucleus is where all the material is, which is going to be coming out in the tail. And then there is the coma, which is a optically thick cloud of material, mostly material which has come out of the nucleus and now surrounds it. And then there is a long tail. And there are often two kinds of tails. One is called as a dust tail, okay, which is not perfectly, but more closely aligned with the comet's orbit. Because remember, the comet is always going to be curving. It doesn't go in a straight line. The ion tail, on the other hand, is something which is always radially outwards from the sun. So the solar wind, which is coming radially out from the sun, sunlight, of course, also coming radially outwards from the sun. These are the things that drive the ions. So these are charged particles, and the dust tail contains mostly uncharged particles coming out of the comet. And the charged particles tend to align radially along the direction of motion of the solar wave. Unlike the nucleus, which I said is very small, and the coma is a bit bigger, the dust tail can be enormously long. Enormously meaning 100 million kilometers, 150 million kilometers. Numbers like this are possible, right? It's very, very long. So we've actually, meaning ESA has succeeded in landing a probe onto a comet. Okay, and they even have photographs from the surface of the comet. And this is the comet, got some name, 67 ECG comet. And Rosetta is the name of the probe that was sent to study this comet. So this is somewhat similar to what we thought, but the proportion of water ice seems to be less than what the theories of comet formation claimed. Okay, so there is water, no doubt. Okay, but there is also dry ice. There is sand kind of thing. So it's one of the more popular names for this kind of models was dirty snowball. So which is take a lot of snow, mix it with a lot of mud. Okay, what you get is the comet's nucleus. So the ice proportion is less than expected, but otherwise it is quite similar. There are also a lot of volatiles in there, gases which are trapped within the comet. The comet doesn't have very high density. That also they were able to measure. So it's like very fluffy snow. Okay, it's not very densely packed, and therefore when it comes close to the sun and starts evaporating, very rapidly it begins to lose mass. And the short period comets will not last forever. Okay, they will eventually lose so much mass that they will disappear. Okay. Kuiper Belt. So Neptune, Pluto is one of the objects within a region of space known as the Kuiper Belt. And this is a disc-shaped region beyond Neptune's orbit, and it contains many small icy bodies. And these are called Kuiper Belt objects. And Pluto is just one of them. There are several others that have been discovered. So it's the home to Pluto and other dwarf planets. And it is the source for the short period comets. So eventually, due to some perturbation, likely due to Neptune or one of the other outer gas giants, some piece of rock gets pulled into the solar system, and then it becomes a short period comet. It extends from about 30 AU to about 50 AU from the sun. AU, remember, is the astronomical unit. It's the mean Earth-Sun distance. So there are analogies to the asteroid belt and the Kuiper belt. Okay, so the asteroid belt is between the orbits of Mars and Jupiter. Okay, whereas the Kuiper belt is outside the orbit of Neptune. Remember that the asteroids have a completely different character relative to the Kuiper belt. They are mostly rocky objects, whereas the Kuiper belt objects are mostly icy objects. So, of course, there are rocky objects also there. Like Pluto is covered with ice, but it is a piece of solid rock. But the parallels are there, that just like you have more rocky objects, thousands and thousands of them inside, you have thousands, millions, billions, trillions outside in the Kuiper belt. Okay. So just like we landed a probe on the comet, there was a probe that was landed on an asteroid in order to study its properties. Asteroids are quite rich in metal content. Okay, they have they're quite sort of iron-rich asteroids are there and so on. So there are talks that in the future that one may be able to mine asteroids for some precious metals. Okay, so beyond asteroids, beyond Kuiper belt, beyond everything, there is something known as the Oort cloud. Now, this is just a theoretical formulation. It's a cloud of icy bodies surrounding the solar system, and it goes from about 2,000 to 100,000 AU from the sun. Okay, believed to be the source of long period comets, and this contains trillions of objects larger than 1 kilometer. And it marks the outer boundary of the solar system. Now, this 100,000 AU is a very large number. Okay, the distance to the nearest star is about 270,000 AU. So it's about 1/3 or more than 1/3 of the way to the nearest star is the Oort cloud. Of course, remember, it's all going to be very dense. So although it says here contains trillions of objects larger than a kilometer, because the space volume is so large, the average spacing between these large objects is going to be extremely large. Yeah. So for context, just to show you how much bigger the Oort cloud is relative to the Kuiper belt. So what has been shown here in the zoomed region, so what they've done is they've taken this little rectangle and zoomed it out over here. So this is orange track represents a typical KBO orbit. Pluto's orbit is represented by this. No, Pluto is this yellow ring. Maybe not. So this is the sun. This ring is Pluto, and this one is a typical KBO orbit. And that whole thing fits in over here, and this whole thing is the Oort cloud. Gigantic, And I don't fully understand what the exact theoretical motivation is for the existence of Oort cloud. There are motivations which show you that long period comets are coming from far away. Okay, they're not coming from the Kuiper Belt. If you sort of trace back their orbit, where they came from, they're coming from infinity. And that is one reason why we say that these are the Oort cloud must exist. Okay. So now coming back into deep inside the solar system, there's something known as zodiacal dust. So these are tiny particles of dust in the inner solar system, and they are primarily produced by asteroid collisions and comet outgassing. And these dust particles tend to scatter sunlight to create something known as the zodiacal light. It's a faint glow visible in very dark skies, contributes to the interplanetary medium, so that what is in between, what is the material in between the planets? It's mostly this this dust. The thing has to be constantly replenished because the larger particles will slowly spiral into the sun. Zodiacal light. This is a picture of the zodiacal light, taken from the site where a new telescope has been installed. It's the Rubin Observatory's telescope, which has been installed on a high mountaintop in Chile. And this faint glow that you're seeing, whitish glow that you're seeing, is the zodiacal light. It's very hard to see. Even from the best sites, you need absolutely clear skies, and you have to watch either just after sunset or just before dawn, and you have to be able to distinguish between what is twilight and what is the zodiacal light. If you can do all of those things, you can see it. I myself have never seen the zodiacal light. Okay. So the Earth has a very unique position in terms of its ability to support life. Okay. And what are the reasons behind this unique position are what are listed. So there is a concept known as the Goldilocks zone or the habitable zone. The habitable zone is a region around a star where liquid water can exist. So it has to be sufficiently far away from the star such that the water doesn't get converted to vapor. And it has to be sufficiently close by that it doesn't freeze into ice. So liquid water is thought to be very important for the kind of life that we have on Earth. It has a stable oxygen-rich atmosphere. Okay. In this one respect, it is absolutely unique in the universe so far. We have found no other planet which has a large oxygen. It has a strong magnetic field, and that protects us from very high energy charged particles coming out of the sun. Plate tectonics regulates the carbon cycle. Okay. So a large amount of carbon is trapped. The reason why we have so much oxygen in the atmosphere and so little carbon dioxide is because most of the carbon dioxide has been trapped. Okay. And these plate tectonics help in regulating the carbon cycle. So it helps in creating land masses which are sufficiently close to the equator that they can absorb a lot of carbon dioxide and convert it into carbon. It has a large moon. At least in our solar system, this is a pretty unique situation that you have such a massive and nearby moon to a rocky planet. Okay. In fact, no other, except for Pluto, which has a large moon, like we saw. There's no other planet with such a large relative to the size of it. And this stabilizes the Earth's axial tilt. You can contrast this with Mars. Because Mars does not have, right now it has an axial tilt similar to that of the Earth, okay, but about 23 degrees, but its tilt can vary between about 15 degrees to 35 degrees over time scales of millions of years. So it sort of just moves up and down like this. And because of that, the seasons are not stable. and the temperatures keep changing and so on. So Earth has a very, very stable axis of rotation. Although, as we shall see, it does precess. The axis doesn't point in the same direction all the time. It changes, but the tilt remains the same. It has a diverse range of environments supporting the biodiversity. It has a complex organic chemistry. This is mainly all carbon-based chemistry. Presence of a protective ozone layer. Okay. This formed fairly late in the history of the Earth. Earlier in the old days, billions of years ago, when there wasn't enough oxygen on the Earth, it was all carbon dioxide atmosphere, there was no ozone layer. Therefore, UV radiation could freely hit the surface. But now we have that ozone layer. And all of these factors together are not found anywhere else in the solar system for sure. And one of these, stable oxygen-rich atmosphere, we have not found anywhere in the universe or anywhere in our galaxy as we have searched. Okay, so before we leave the solar system, a brief summary. There's a central star, only one star in our system, not a binary. There's the sun, there is the inner solar system, which contains these rocky planets, the outer solar system, which contains gas giants and ice giants. And then trans-Neptunian region contains the Kuiper Belt, and the outer boundary is formed by this Oort cloud. Okay, so when we go look at other solar systems, we have to remember the diversity of within our own solar system. Okay, so within the same solar system, we find wide range of sizes, wide range of chemical compositions of the planets, wide range of environments. Okay, very hot planets to very cold planets. Numerous moons. The moons themselves have very different physical characteristics. Around the gas giants, you have a complex system of rings. And there are a large number of small bodies, asteroids, comets, and trans-Neptunian objects. Okay. So keeping all of these things in mind, one begins the search for extrasolar planets. So what are extrasolar planets? Of course, these are planets orbiting stars other than our sun. They're also called exoplanets. The first detection happened only in 1992. But now, as of this month, we have more than 7,000 confirmed exoplanets. So early speculations were, of course, there. Ancient Greek and Indian philosophers talked of concepts of other worlds, okay, beyond the Earth. But of course, they didn't specify in which direction this other world is or how far away it is and so on. But that concept already existed in philosophy. In the 16th century, Giordano Bruno was the first philosopher or scientist who suggested that there was an infinite universe and there were lots of inhabited worlds spread all throughout. In the 1950s and to 1980s, various attempts were made to detect these exoplanets, but none of them could be confirmed. So claims were made. When other people tried to look, they said, no, we can't see what you're seeing. So it went away. So why is detecting exoplanets so difficult? Correct. So they're much fainter than the associated host star. So the glare of that host star simply drowns out the light of the comet, light of the planet. So it is extremely difficult to detect exoplanets through direct imaging. So you have to use other indirect techniques. In 1992, a planet was discovered in orbit around a pulsar. Okay? Because this pulsar had been studied for many years, and these people were able to find the presence of an object which was perturbing the pulsar. In 1995, Michel Mayor and Didier Queloz discovered 51 Pegasi b, the first exoplanet orbiting a main sequence star, a regular star, not a compact object like a neutron star. And these discoveries just opened the floodgates. and led to enormous number of discoveries in the field of exoplanets. Okay, so let's look at what are the sort of detection methods that people use when they search for exoplanets. The first is, of course, direct imaging. Can you just try to see if you can see the planet out just outside the glare of the star? Okay. Okay, there are ways to do this, and some more advanced techniques are coming up now. But really, as we said, because of the glare of the host star, this is an extremely difficult exercise, right? The second thing you could do is you could measure the radial velocity of the star. Okay, how will you measure the radial velocity of any star? By measuring the redshift. And so the what will happen is, because the planet is going around the star, okay, and of course in reality both star and planet are going around their common center of mass. So the star cannot stay stationary; it moves back and forth. Okay, so of course there is one configuration in which you will not see this radial velocity, and what is that? Yes. So when the plane of the orbit of the planet is in the plane of the sky, then the radial velocity component is 0. And so it will move up and down and left and right and so on, but it won't move forward and backwards relative to you. And therefore you won't see any shift in the spectrum. Now, how small a shift can be measured? With the highest resolution spectrographs that we have on Earth, which give you resolutions of tens of thousands, you can measure of the order of a meter per second, 1 meter per second, 2 meter per second oscillations in the positions or in the velocity of the. But of course, you need very high, extremely specialized instrumentation is needed to measure the radial velocity. If you take a prism and spread out the light, it's not going to move visibly. Okay, that's the second technique. The third technique is called as the transit technique or the occultation technique. So what you do is, suppose there's a star here and a planet is going around it. If the plane of the planet's orbit is at some point at least intersects the plane which contains the star and ourselves, then you will see the planet pass in front of the star. And that will occult, or it will hide some of the light of that star. And because of that, the star's flux will go down. And then when the planet has left the disk of the star, the flux will go up. And if you keep on observing that planet, then you may be able to determine the period of its orbit. So if you know that, okay, every 3.5 days it will cross, you know exactly when it will come next time, you can keep watching and you can measure it. Yeah. This is currently the majority of planets that we know so far have been discovered via this transit technique. I'll talk more about that later. The fourth technique is gravitational microlensing, and I have a figure a little bit later which illustrates this. But here the basic idea is that if you have a distant object emitting light and a massive object comes in between you and that distant object, then the light from that distant object will be lensed by this nearby object, and suddenly that distant object will appear to brighten. Okay, so it will brighten, and then as this object, as the lens moves away, it will fade back to its original brightness. This phenomenon is known as gravitational microlensing. And by just looking at many stars for many years, people have actually discovered these kind of microlensing events. The next technique is astrometry. This is just a variant of the radial velocity technique because remember, the star will move forwards and backwards, but it will also move sideways and up and down, right? So if you can measure the position of a star very precisely, then, and if the planet is sufficiently massive, you can observe its astrometric drift over time. Now this is very, very small. Okay. And this is, it's very hard to measure in practice. So right now, even with instruments like Gaia, we are not able to find too many planets via this technique. Only a handful have been discovered, but in very, very special conditions. Transit timing variations. This is a very interesting technique. So you're measuring the timing. You've seen one planet and you say that, okay, every 3.5 days it transits. So you're waiting and you have predicted that, okay, today at 10:45, 47 seconds, transit should start. Okay, and it doesn't start. Starts a second later, second earlier. Okay, and you think, what's going on? Is my orbit correct? And then you do it again, make the next prediction. Again, your prediction seems to be coming wrong. So what is happening here is that there is another planet which is perturbing the orbit of this planet. That planet may not be exactly in the same plane. So you're not seeing that second planet transit, but it is affecting the transit times of the planet that you're observing. And that provides indirect evidence for the existence of these exoplanets. Again, this is a very specialized technique, difficult to implement, and therefore only a handful of planets have been found via this technique. Okay, so direct imaging, Fomalhaut B. Okay, so there is a star called Fomalhaut, okay, which is sitting in the center, and it's represented by this. So what do you think? Why do you think we are not seeing the light of the star itself? You're blocking it. Okay, so there is known as something known as a stop, which can be placed strategically, which sort of blocks the light of the central star. And this kind of instrument is known as a coronagraph. Okay? From the instrument, it was originally designed for studying the solar corona. That's why coronagraph. To study the solar corona, you have to block out the light of the sun so that you can see the corona. So similarly, here they blocked out the light of the star. It's a very bright star. Fomalhaut is one of the brightest stars in the sky. And then they took an image in 2004 and they took another image in 2006. And in this corner of the image, they found out there was something here in 2004 and something here in 2006. Okay? And then they said, oh, we found the planet. They made the announcement. They calculated the orbit and they said, okay, in 2008, probably it should be here. And this planet later on, I mean, I discovered this yesterday, incidentally, when I was just confirming, just reading up on Fomalhaut B. This planet has now disappeared. So there are various theories. One theory is that there's a lot of dust around here. So maybe that is obscuring the planet. Or maybe it was just some debris that was hanging around and that has now scattered. And so the planet has disappeared. So in any case, this first example of direct imaging Fomalhaut B has now failed to live up to expectation. But there have been one or two other cases where we have been able to do direct imaging where the detection seems to be more robust. So there is a dust disk across around the planet, around the star. Okay, this is a very luminous star. So the dust disk cannot survive close to the star. So it is very, very far away, meaning it's like the Kuiper Belt region of relative to the star. So it's very far away, but there is a fair amount of dust, and that dust is brightly emitting in the infrared bands. Okay, but it can also be seen obscuring in the optical bands. So there is a lot of hot dust which surrounds the star, and this planet seems to be moving, finding its way through the dust. So it may just be a planet in formation. So it may just, so although that asteroid debris or debris idea is there, so maybe we know that rocky planets form from debris. So maybe this is just the first attempt at trying to form a planet within this system. And later on, maybe a million years later, there'll be 7 planets here or whatever.
how long will they track this? 2004, 2006?
I think they've given up on this because these kind of observations can only be made with the Hubble Space Telescope, and Hubble Space Telescope time is very competitive. You can't get it easily. So if it were a confirmed exoplanet, they would have had lots of opportunities to track it. But now I think, I don't know, I have to check definitively whether it's still being observed, but most likely not. Okay, so the radial velocity method. It measures the star's wobble due to the planet's gravitational pull detected through Doppler shift in the stellar spectrum. And it is obviously more sensitive to more massive planets which are close to the star, because those are the things that will create the largest radial velocity variation. So the key equation here is this one: k is equal to 2 pi g over p. P is the period of the planet's orbit raised to 1/3. MP is the mass of the planet, ms is the mass of the star, and sin I is the inclination of the orbit. Okay. Naturally, if you plug in I of 0, sin I becomes 0, and there will be no radial velocity. K becomes 0. Right? That's when you have that face-on condition. But at any non-zero value of the inclination, you will begin to see this semi-amplitude of the radial velocity variation. Why does this not depend on the radius of the orbit? Because the variables seem to be mass of the planet, mass of the star, and the period, not the distance of the star, of the planet from the star. Sorry? Yes, in what way? Correct, correct. So Kepler's third law, right? So because of Kepler's third law, that period is indirectly sitting, the distance is indirectly sitting into the period. Yeah? The period, of course, just depends on what is the mass of the star and the distance. Okay, so that is the reason distance is not appearing in this equation. Okay. So this kind of technique requires very high resolution spectrographs. Quite tough to carry out. Nevertheless, there are a number of specialized instruments that have been built. These are called like planet hunter type instruments, which are installed on several telescopes across the world. And they have kept on detecting newer and newer planets. They try to look at nearby stars only, because then the stars are likely to be bright, and they are likely, therefore, the spectrum. See, what happens is when you take a high resolution spectrum, you are spreading the light into many, many channels. So unless the original light is very bright, you will not get sufficient signal to noise to reliably measure the shifts in the spectrum, unless you have a bright star. So they do nearby stars, bright stars, and so on. The other technique, on the other hand, the transit occultation method is completely different. It detects dimming of starlight as planet passes in the front. It provides information on planet size and orbital period. It can detect smaller planets than the radial velocity method. Okay, and we should see that, because what happens here is that here with this technique, you can not only measure the mass of the planet, okay, but you can measure the radius of the planet, which is really interesting. And because this is a pure occultation technique, delta F, which is the change in the flux relative to the flux due to the occultation, due to the transit, is Rp over Rs square. Because if you have a uniform disk, okay, it has area of pi r square, that's the star's radius, and the planet will be pi RT square, that will be the radius. So the ratio will be proportional to the square of the radius.
Ratio.
Huh?
It will be measure the ratio.
No, but you can measure F.
Yeah, so delta F by F we measure.
Correct.
Gives us the ratio of the radii.
Yes.
Planet.
Yes. Yes.
Do we know the
Do we know the radii of the star? Yes. So if it's a main sequence star, we don't know it directly. We can't measure it. But what we have very accurate stellar models, which can tell us that the radius of the star is going to be so much. So we know that, and flux we know. So we know this quantity. We also know what is RS from models, and therefore we can get an RP in kilometers. Yeah. So it can detect Earth size and smaller planets with accurate photometry, and we'll work through a small problem on that in a minute. It allows for atmospheric characterization through transmission spectroscopy. So if measuring the radius wasn't good enough, you can measure the composition of any atmosphere that the planet has. This is just, to me, is really staggering, because and we went from the first discovery in 1995 to the first atmospheric characterization in 2002. It really boggles the mind, and I'm going to show you some examples of it. It enables detections of multiple planets in the system. So then one transits, then you see another transit, but as per your orbit calculation, it should not have occurred for another 2 days or 5 days. And then you say, oh, this seems to be another planet. So then you calculate its orbit, and then you find third planet, fourth planet, fifth planet, find a whole system. That has also been done, and can be used for large-scale surveys of many stars simultaneously. So in this sort of situation, if you want to find transits over long periods of time, what would be the most effective strategy? I'll give you a telescope. What will you do with that telescope in order to find the maximum number of planets? Because some planets will transit every 2 days, some will transit every 30 days, some will transit every 2 years. Okay? You want to find all of them and everything in between. What strategy will you adopt? Sorry? Continuous observations. That's the correct strategy, which is you take a part of the sky, okay, and just keep on observing that continuously. Integrate, take an image, integrate, take an image, integrate, take an image. And then if you have many stars in your field of view, then some of them will brighten and fade depending on the transit. Of course, you have to worry about some stars being genuine variable stars. So the flux is changing because of variability of the star itself. But there are ways to rule out that possibility. And then you can find it. Okay. So if Jupiter were in a one-day orbit around the sun, what fraction of the sun's light would it block during a transit? So to calculate that, I'll give you a rule of thumb, which is Jupiter is to order of magnitude 10 times the size of diameter of Earth. And the sun is 100 times the diameter of Earth to order of magnitude. So what fraction of the light will get blocked? You have to assume, of course, that in such a close orbit, Jupiter survives. Actually, it'll get vaporized. But forget that for the moment.
I would
1 by 100. Yes, 1 by 100. That is.
it's in a one-day orbit around the sun. So it's at a certain distance.
Yes, yes.
What fractions block at Jupiter's distance?
So if it were at Jupiter's distance, that means 5 AU, not in a one-day orbit, but in a 12-year orbit, okay, would it be different?
We're looking at the sun from really far away.
Yes, yes, yes. So assume this is like an extra, you're an extra solar observer.
Very
It won't change because the relative distance to Jupiter at 5 AU and the sun, which is whatever distance d plus 5 AU, that change is so small that it doesn't matter whether it's at 1-day orbit, 12-year orbit, 7 years. The only reason why we chose 1-day orbit is because you'll be able to observe many transits. If you're in a 12-year orbit, you'll be one transit every 12 years. So that's just. So at Jupiter's distance, again 1% will be blocked. Okay. So this is the picture of the first detection of the chemical composition of the atmosphere of an extrasolar planet. So the idea is as follows, that there is this planet which is going around a star. Okay. It's in a 3.5-day Earth days orbit. Okay. Very close to the planet. But if you take its spectrum, okay, and when you take the spectrum over here, when it is transiting, when it is here, you don't see much light from it. So you will see the spectrum of the star itself. But when it is here, the spectrum alters slightly. And why does it alter? Because now light is passing through some of the light is cut off, which doesn't change the spectrum. But some of the light is passing through the atmosphere of the planet, which changes the spectrum. Particularly absorption due to additional absorption due to the planetary atmosphere tends to occur. And this is that additional absorption. The normal absorption is shown by over here. There was some absorption due to the star itself, but for a particular chemical, the absorption increased during the transit and decreased when it was out of transit. And you can take this spectrum repeatedly because it's in a 3.5-day orbit. Every 3.5 days, you keep taking a spectrum so that you can stack many spectra together and get a high signal to noise detection. So extraordinary. So it turns out, I think this planet had a lot of sodium chloride in its atmosphere. And these absorption lines were caused by that. Okay. So they named the planet Osiris. And there is a friend of mine called Alain Lecavalier, who works in Paris. And he said, now that we know the atmosphere, we know the spectrum of the star, we know the spectrum, we know the atmosphere of the planet, I can now create a scientifically accurate movie of what a sunset on that planet will look like. Sunset or star set, if you want to call it, because it's not our sun, it's that sun. So I'm going to try and show you this. It's a fairly complicated exercise because on this Mac, that video was not running. So he says that the color of the atmosphere, etc., everything is has been correctly modeled. I'll just play for it again. So in about 7 years, we went from the detection of the first exoplanet to this.
There are not much clouds in the sky.
It's a gas giant kind of thing. So that is why the sun is not setting abruptly. There is no hard horizon. It is sort of just changing color and disappearing. Because they even built a atmospheric model. We know what is the temperature at that distance from the star. We know the chemical composition. We know the radius of the planet. We can make a guess as to its mass. Okay, we'll put that mass in and so on. So it's quite a complicated exercise. And I think they have a paper about this, this particular work. Okay, so let us go back to our So here we are. Okay. Now we can do better because now we have the James Webb. This was 20 years ago. The James Webb Space Telescope is up in orbit, and it has also the ability to detect exoplanets and study them. So this is a particularly common kind of exoplanet. It's a hot gas giant. Okay. Remember, even with the transit technique, it is easier to detect short period objects and massive objects, because massive objects lead to and have a larger radii and therefore lead to a big drop in flux, which is measurable. Okay. So by big drop in flux, one means here 1%, 2%, so on. It's not very large, but yes, quite easily measurable. So what is shown in this is the typical light curve for a transit. So the light is at 100%, you're seeing the star. And then over here, the star gets obscured. So now it is transiting. During the transit, the flux is quite low. And then it brightens up again and comes up. Now, why does this take time? Because this is a very large planet. So it doesn't go off the disk in 1 second. It takes some time to leave the disk. Right. This has an atmosphere, and they've been able to study the atmosphere. But what they've also done is that they've also know that because this orbit is so close to the parent star, it is tidally locked. Okay. What does that mean? That means that the period of rotation and the period of revolution is the same. So this particular planet shows the same part, same half to the parent star, and so that is permanently in daylight, and the other side is permanently in darkness. So there is something known as a terminator, which separates the morning side from the dark, or the bright side from the dark side. And there is a place where the star is rising, and there is a place where the star is setting. So those are called the morning and evening terminators. So what they did was, like when the planet enters this, right, this part will enter first. So the morning part will show absorption when it is entering the transit. And when it is leaving the transit, the evening part will show absorption, not the morning. So they said, okay, let us measure the spectrum at these times only. And many times we'll do it with many orbits. Every 3.5 days, we'll keep on repeating the exercise so that we get good signal to noise. And let us see if there is a systematic variation in either the chemical composition or the temperature of the atmosphere. And this is what they found. So this thing has water, it has carbon dioxide. Okay? But the height of the peaks is different in when fit model morning. So morning is this curve and evening is this curve. So the amount of water vapor in the atmosphere seems to go up in the evening and it goes down in the morning. So quite remarkable result from the best fit models. So now we are finding planets, finding their atmosphere, modeling their temperatures, modeling which side. And they now have worked out a theory of there must be some cold winds which are blowing from the dark side onto the bright side in different directions. That must be leading to some cooling and so on. So quite an interesting experiment. Very recent, by the way. This result was published a month back. Okay, so now let us go back and talk a little bit about the preeminent transit extrasolar planet observatory. It's called Kepler, launched in 2009. Initially, they said this is a 3 point, yeah. No, you can't measure the mass of the planet exactly, right? But there are various ways in which you can constrain the masses and so on. But the densities don't vary widely. Okay, if you take a least dense planet on Earth, planet in our solar system, that is Saturn, that's density is 0.9 grams per cc. And Earth is about 5.6. Okay? So that's the range. Within a factor of 5 or 6 is the range. So even if you take a midpoint of the density, you'll be off by a factor of 2, 3 at the most.
The mass of the radius from
You can, yes, of course. Yeah. So if it is possible to do the radial velocity measurement for this star, yes, you can get the mass through the radial velocity, you can get the radius. And this has been done for several stars. But using the transit technique alone, you can get the radius perfectly, but you can't get the mass. And using the radial velocity technique, you can get, subject to that sin I factor, you can get m sin I quite accurately, but you can't get the masses of the, you can't get the radii of the orbit. Okay. So this use the technique that you were just talking about, which is just stare at one part of the sky for a very long time. So it basically pointed in one direction. It observed 530,000 stars, and it discovered 2,600 confirmed exoplanets. So approximately 1/3 of the planets that we know are discovered by Kepler, and they are by necessity in one small patch of the sky. And it really revolutionized our understanding of exoplanet populations. One cannot imagine how much impact this thing has had. So this movie I can play. So this is supposed to be our galaxy. We're sort of zooming in. This is the sun, and Kepler is near Earth, and it is looking in this particular direction. This arm is known as the Cygnus arm of the Milky Way. So it is going to detect planets around stars all along the way, and of course within that part. So all those 500,000 or so stars that it is staring at are in one particular patch of the sky. And so if you look at a distribution of extrasolar planets on the whole sky, you'll find one Kepler patch where many of the planets are. So what are the key findings from Kepler? Planets are common in our galaxy, approximately 1.4 planets per star, okay, at least. This is based on some modeling. Okay, so this they say is the lower limit. There could be more. So planets are clearly common in the galaxy. And as we shall see in a minute, that has some implications. Small planets are quite abundant. We'll look at in a minute at what super Earths and mini Neptunes means. But this is just in terms of their sizes. Multi-planet systems are common. It has already discovered potentially habitable planets. Okay. And the Copernican principle seems to apply. What is the Copernican principle? Anybody knows? Yes, we are not special. Okay, we are not at the center of the universe. That's the Copernican principle. Okay? And that was extended to our solar system. It was extended to the galaxy, and within our galaxy, Copernican principle applies, which means our solar system is not special in any way. There are millions, billions of such stellar systems in the Milky Way alone. Okay, so there is another satellite. So Kepler had a 9-year mission. Now it is shut down. But there is another mission which is active, which is called TESS, Transiting Exoplanet Survey Satellite. It launched in 2018. This one doesn't look at one patch of the sky, but it says that, okay, I'll look at multiple bright stars uh, around there's an all-sky survey focusing on nearby bright stars. It is expected to find thousands of exoplanets. And with Kepler and very likely with TESS, what they tend to do is that they don't announce every new planet that they find. Okay? Because all part of one collaboration, they will suddenly have a paper in which they will, I think Kepler once published 1,300 planets in one go, one day. Okay, here 1,300 planets discovered, just to have a higher impact. Designed to find promising targets for follow-up studies. Okay, so micro lensing. So this is another technique. So here is your, as I mentioned, if some moving object could be another star or could be some massive dark object, okay? If it passes between you and the star in the background, then the brightness of the star will brighten dramatically. And over here, the most important thing is geometry, not so much the mass of the lens. Okay? So even if you have a low mass star that passes in front of a highly luminous big star, this one can lens its light quite effectively so long as the alignment is perfect. And the brightening is very short and very dramatic because of the lensing effect. Now, if this thing has a planet, that planet can create its own peaks on over and above the peaks that you see in the stellar profile. And the advantage of this technique is that your star is already brightening and the planet is brightening over and above that. That if the planet were only brightening by itself, it would be harder to detect because the total flux would be very low. It would be drowned in the noise. But now this is like a small wave sitting on top of a big wave, and it becomes easier to detect. Nevertheless, this technique is very difficult. Okay, it's not an easy technique to implement in practice and has not been very successful. Okay, so exoplanet size distribution. So there are certain definitions. Terrestrial planets means less than 1.6 Earth radii. Then you have super Earths, which are up to about 2 Earth radii. Then you have the mini Neptunes, or Neptune-like as they are called, 2 to 4 Earth radii, and gas giants, which are greater than 4 Earth radii. Yes, they could be terrestrial, they could be rocky, but not necessarily. They could be gaseous also. Last three categories are in roughly equal numbers today. Okay? This is very hard because both for the radial velocity technique as well as the transit technique, a big massive planet is easier to detect. Something like this is easy to detect. And that plays such a big role that we have to apply very strong correction factors when we try to estimate the number of planets. These things are quite rare, it turns out. They're very easy to detect. If it's there, you'll see it. Whereas these things are much more common, but they are harder to detect because the accuracy of your flux measurement or your spectral shift measurement has to be very high. Okay, so this is the current exoplanet census. Total confirmed exoplanets greater than 7,000. Planetary systems are greater than 800. Super Earths and mini Neptunes are the most common. Hot Jupiters are rare but easier to detect. And Earth-sized planets in habitable zones. Okay, that means terrestrial planets in habitable zones. There are several candidates. So quite promising. Okay. So I think we will stop here because I have another meeting starting in a minute. Any questions from today?